It is my great pleasure to give a talk in joining Harvard Engineering Virtual Conference. I'm Yeong-Do Park from Dong University in South Korea, and I will give a full presentation on behalf of co-presenter Dr. Chang-Yong Lee from Hyundai Steel. My speech today addresses the understanding of LME cracks in resin spot welding and proposed approaches for liquid metal embrittlement pre-welds. No surface cracks at the weld joint area are allowed because of the high risk of reduction in the joint strengths, such as tensile shear strength or cross-tensile strength. Our research group was able to capture the real-time LME cracks using the high-speed video cameras in the year 2016. You can observe the continuous LME crack initiation and growth throughout the entire welding time and holding time. Based on the observed LME cracks, the following three factors are the main prerequisite to form LME of steels. First, liquid zinc in contact with the steel. Second, overcritical tensile stresses. And third, base metal microstructure. When these three conditions are met at the same time, the LME crack will occur. Based on these prerequisites, liquid zinc, base metal microstructure, and tensile stresses. For a better understanding of liquid metal embrittlement cracks, I will try to explain the effect of zinc coating on the LME cracks. Secondly, effect of base metal microstructure on the LME cracks. And lastly, effect of resin spot welding process on the LME cracks. After that, I will propose feasible approaches for LME-free weld with first control of zinc coating, and second, control of base metal microstructure, and lastly, optimization of resin spot welding processes. In part 1, let's make a deeper understanding of LME cracks. Firstly, effect of zinc coating on LME cracks. In the year 2015, we made an investigation for the effect of different coating types on LME cracks. We made resistance spot welds with increasing current, which results in increased nugget diameter. Then we compared the maximum LME crack lengths in the same nugget diameter. The result shows GI coating is most susceptible and GA coating, lastly, easy coating. Hong et al. Also found that silicon in the steel delayed the dissolution of the iron into the coating from the steel, which suspended active formation of alpha Fe zinc layer. Then it could not prevent the steels from contacting liquid zinc during the welding. So there is an underlying mechanism of the effect of zinc coating microstructure on the LME crack occurrence. To understand the underlying mechanism of zinc coating microstructure, Caliber tests at different temperatures starting from 700 to 900 degrees Celsius with different holding time have been done and correlate between zinc coating microstructure and LME behavior. The specific temperature and holding time combination shows the more prone to LME cracks than others. The graph shows the stress and strain curve of testing temperature at 800 degrees Celsius. The large reduction in strain with the GA-coated sample comparing to the bare steel was observed due to the LME. The reduction in strain due to the LME is called LME onset strain. The less LME onset strain value represents the more sensitive to liquid metal embrittlement. We display the epsilon LME values with the different testing temperature. The largest reduction in strain was observed at the temperature at 800 degrees Celsius, and logical explanation is required for better understanding. We tried to explain the LME sensitivity with the zinc coating microstructure analysis using SEM-BSE mode by analyzing the ex situ phase constituents such as delta, gamma, and alpha. We can predict the in situ phase constituent and phase fraction at each testing temperature. In testing temperature of 700 degrees Celsius, less than 3% of liquid zinc was available, so there was no LME cracking. However, with the increasing testing temperature, large increase in liquid zinc fraction was observed, and 58% of the phase was liquid zinc at testing temperature of 800 degrees Celsius. When we make a relationship between the fraction of the liquid zinc and the liquid LME onset strain, increased LME sensitivity was found with the larger fraction of the liquid zinc. So the largest reduction in strain at 800 degrees Celsius can be explained by high fraction of the liquid zinc for LME cracks. In more details, 700 degrees Celsius with a short hold time, only 5% of the liquid was available, but not in contact with the substrate, which resulted in no LME cracks. At 750 degrees Celsius, about 7% of liquid zinc was available from the entire coating layer, and it made the contact to the substrate stills through the alpha Fe zinc layer and ends up with the LME cracks. However, at 850 degrees Celsius with the hold time of 100 seconds, established a thick and continuous alpha Fe layer with the less or non-liquid zinc. Then there was no LME cracks. In overall fraction of liquid zinc and continuous layer of alpha Fe zinc are important factors for LME cracking mechanism in zinc coating. We can express this with the water tank analogy. Water level represents the fraction of the liquid zinc, and water tap represents the layer of alpha Fe zinc, which are the flow channel. At 700 degrees Celsius, 1 second hold time, due to the very less liquid zinc and continuous alpha Fe layer, there is no LME cracks. Same for the 50-second hold time condition. However, higher temperature at 850 degrees Celsius with the 50-second hold time, both conditions of liquid zinc and breakage of alpha layer ends up with the LME cracks. For similar case, 800 degrees Celsius, 1 second hold time condition provides large fraction of liquid zinc and continuous alpha Fe zinc layer. The following are the summary of the effect of zinc coating on LME cracks. The LME sensitivity is governed by the fraction of effective liquid zinc. LME is influenced by the breakage of alpha Fe zinc layer, which makes the direct contact of the liquid zinc into the substrate steels. High silicon in the steel delayed the dissolution of iron into the zinc coating from the steel, which suspended the active formation of alpha Fe zinc layer, more susceptible to the LME cracks. So fraction of liquid zinc and alpha Fe zinc layer are the key factors from the zinc coating side. Secondly, the effect of resistance per welding process on LME cracking. As part of the welding process, electrode geometry is well known as a key factor for LME cracks. The results suggest that the radius of electrode is most critical design parameter which control the critical stress for LME cracking. Moreover, the larger tip diameter and higher radius of the curvature display the less maximum stress level, which results in the lower LME sensitivity. This is attributed to the fact that the radius type electrode provides the benefits of increase in both radius and electrode tip diameter. We also investigate the effect of number of welds and electrode degradation on LME cracking. When the first weld was made with a high current level, which turns into the large LME cracking. With increase in weld number, dramatic reduction in total crack length and maximum crack length up to around 160 welds were observed, and further welds shows relatively low levels of LME cracks. Since the surface temperature known to be directly related to the LME cracking behavior, peak temperature was measured with the IR thermography and recorded at each weld. The surface peak temperature also shows large drop until 160 welds and remains low level until the 400 welds. With increasing number of welds, it increases the diameter of electrode imprints, which is due to the changes in geometry of electrode surface. Also, surface peak temperature decreases dramatically up to the 160 welds due to the changes in electrode radius and less thermal stress with the number of welds. Finally, the decrease in maximum LME crack depths up to the 160 welds can be well explained in conjunction with the similar behavior with the peak temperature. So geometrical factor with the increased contact area is more dominant factor of less LME sensitivity than metallurgical factor with number of welds. Effect of total heat input was investigated with the varying mild sheet steel thickness, number of stacks, and extended welding time. Thicker mild sheet and increased number of stacks increase the level of maximum crack length. However, the extended welding time provides the largest effect on LME crack severity. Therefore, the similar combination with the three-sheet stack up and extended welding time combination showed most severe LME cracks. To extend the knowledge of LME cracking mechanism, further studies on reasons of LME cracks at different locations of spot welds and differences in LME crack lengths with the location has been carried. The study was done with the systematic increase in welding time to understand the thermomechanical interaction for LME cracks. When the welding current starts to flow, the temperature of the entire weldment increases. However, the electrode and sheet surface start to make a new contact, which ends up with a sudden temperature drop at the new contact surface, since the electrode is cooled by the coolant. Several physical electrode sheet contact has been observed at each different locations, and sudden temperature drop at the different location and different time during the welding time. By performing the simulation with welding time of T0, T2, T1, T2, and T3, and T4, new contact between electrode to sheet surface established the sudden temperature drop which satisfied the thermal gradient for the tensile stresses. So each time, welding time, it established the thermal gradient and tensile stresses. With increase in welding time, these four steps of electrode to sheet, sudden temperature drop, thermal gradient, then tensile stresses, and LME cracks occurs toward to outer boundaries. These four steps of the LME cracking mechanism well explains the LME cracks in different locations. However, there is a question that why different crack lengths observed in different regions of electrode to sheet interfaces. To answer the question, we need to observe the stress distribution in conjunction with the transition of electrode radius from R1 to R2. Within the R1 phase magnitude, the duration of the tensile stress is relatively short. However, when there is a R2 phase contact has been made, the duration of the tensile stresses become very long and large accumulation of tensile stresses could be possible. Based on the simulation data, we have measured the duration time of thermal gradient and tensile stresses at R1 radius zone and R2 radius zone respectively. With the R1 transition zone of the electrode, the tensile stresses and thermal gradient exist for the shorter time. In R2 transition zone, the duration of thermal gradient and tensile stress are relatively longer. So the duration of tensile stress and thermal gradient would correlate to the differences in crack length with the location. To summarize the effect of resin-spot welding processes on LME cracks, heat input has a direct relation to LME cracking behavior. Sudden temperature drop as a result of the electrode to sheet contact establish the thermal gradient and tensile stresses for liquid metal embrittlement cracking. As the radius changes from R1 to R2 in dome-type electrode, sudden temperature drop occurrence has been delayed so that the tensile stresses accumulate at the location finally develop into the large LME cracks on the shoulder region. Overall, the geometry of the electrode, welding current, welding time, and electrode force influence the thermal gradient and tensile stresses of the electrode sheet surface. Therefore, the welding parameters have strong relationship to the location and size of LME cracks. Finally, the effect of base metal microstructure on LME cracks. Year 2018, one review paper summarized the LME sensitivity with the different steel grades, which gives the potential possibility of relationship between base metal microstructure and LME cracks. This year, Rinpoche et al. Reported the liquid metal penetration only occurs in random high-angle grain boundaries, where its propagation path is a function of misorientation angle and stress component perpendicular to the grain boundary plane. In contrast, low sigma coincident site lattice boundaries such as sigma 3 and sigma 5 to 9 resist to the LME cracks, even at the maximum stress component. Our research group also found that there is a large difference in LME crack sensitivity between medium manganese steel and DP steels, even with extended welding time. In case of medium manganese steel, large shoulder crack has been observed with extended welding time. In case of DP steels, no large shoulder crack were found even in extended welding time condition. Now, from here, part 2, proposed approaches for the liquid metal embrittlement free welds. I will try to explain in 3 ways. First, control of zinc coating microstructures. Secondly, control of base metal microstructures. And finally, optimization of regions for welding processes. First, proposed approaches for LME-free welds. Control the zinc coating microstructure. Let's control the fraction of liquid zinc and alpha Fe zinc layer. Formation of continuous alpha Fe zinc layer is important for the suppression of LME cracks. Minimize the liquid zinc fraction to avoid a direct contact to substrate. Optimization of initial zinc coating microstructure with coating alloy design, such as low silicon and annealing parameters. Here I have a full combination of the liquid zinc and alpha Fe zinc layer. First case, no liquid metal embrittlement due to the no liquid zinc is available. In second and third case, with available liquid zinc, non-uniform alpha Fe zinc layer will open up the channel for direct contact of the liquid zinc to steel substrate. When uniform continuous layer alpha Fe zinc layer forms at the interface, suppress the LME cracking. Also, the fragmentation of alpha Fe zinc layer due to the external tensile stress also can induce the propagation of the LME cracks. Second proposed approach for LME-free welds by control of base metal microstructure. Let's control the grain boundary energy. In an austenitic steel, grain boundary engineering approach can be feasible method to reduce the LME cracks. As Rinpoche et al. Proposed this year, that by suppressing a lot of random high-angle boundaries and applied grain boundary engineering technology, we can consist of a lot of special CSL boundaries, which ends up with the suppression of LME cracks. However, grain boundary engineering in ferritic steels is still a challenging task for LME reduction. So, the optimizing grain boundary energy to control the grain boundary diffusion and wetting behavior of zinc can be alternating option. Finally, proposed approaches for LME-free welds. Optimization of resin spot welding process. Let's control the critical stress buildup during the resin spot welding. Controlling the tensile stress buildup using optimization of process parameters such as welding current, time, and electrode force can be possible. Heat input dependent hold time adoption, which is proposed by Hon et al. This year, should be used to avoid LME cracks during the spot welding. The optimization of electrode geometry can mitigate the stress buildup over the critical limit. However, it is not an easy option for the automotive industry to adopt. Using multiple schedules to minimize the critical stress buildup needs further investigation. Let's control the fraction of liquid zinc, alpha Fe zinc layer, grain boundary energy, and stress buildup for LME-free spot welds. I'd like to acknowledge the experimental help from my graduate students and also support from the analysis from the KITEC, and finally financial support and discussion from the Hyundai Steel. Thank you very much.